everyone. My name is Nagy, and this is what I'm going to be talking about. And better late than never, I just realized that unlike the many conferences I've recently participated, blockchain technology might not be common knowledge with this audience. So just for a quick survey, could I have a quick show of hands if you're familiar with Bitcoin and its basic architecture? Could you raise your hands? Okay, so thank you. I will adjust my emphasis accordingly. So what I'm going to be talking about is yet another distributed file system, a storage system, which differs from the ones that you're familiar with in that it is resistant and secure against so-called Byzantine faults. So usually the distributed file systems that we're dealing with are secured against crashes. So some nodes can go offline, they may lose information, and so on. But in this case, we are dealing with nodes that are malicious, that want to deliberately sabotage the system. And basically, the trust model that we are addressing here in Swarm is that you trust the software that you're running, you trust the design, you trust your own computer, but nobody else. In particular, you don't trust the other nodes to do what they're supposed to do. Rather, if you want them to do something, you kind of incentivize it. So there are incentives to behave well. There are disincentives to behave not so well. And there are some strong security measures against behaving destructively. So, what's the purpose of this design? Firstly, it's keeping the permanent record safe and accessible. So in the system, Ethereum, it's a distributed system which is a departure from the traditional server-client model of distributed computations. So every node here, it has the same architecture. It doesn't mean, of course, that some are not more, so some are not producers and others are not consumers. Of course, there's a difference between the usage patterns, but no matter whether you're running a data center or a smartphone, the basic architecture of the application that you're running is the same. So there's no architectural distinction between service providers and service consumers. So the things that you run on these systems are called Đapps, or distributed applications. And it's important to make those available securely and timely and in a reliable fashion. The other purpose is a fair allocation of storage and bandwidth. So each participant provides storage space and bandwidth to this network, and they also use it. And the purpose of this design is to make sure that whoever is contributing gets compensated. There's also a very important part to provide reasonable redundancy to make sure that as nodes come and go, important information remains available and accessible, and integrity protected, of course. And finally, it's the authenticity and integrity of the content, that if something claims to be something, it indeed is that. So that's the design goals. And here's the basic architecture of this system that we have built, Swarm. It is a very clean design in the sense that we have well-separated layers that talk through very, very small and simple APIs. And there's very little, actually next to none, cross-layer communication. So the basic layer is a storage of chunks. A chunk is a fixed-sized block of data. It's 4 kilobytes or less, and they are accessed through their hash, so their cryptographic hash. So the base layer of Swarm, all it does is that if you ask for a chunk, then somebody will provide it to you. That's the basic contract, that's all it does. Above that layer, we have a random access arbitrary length files. So they are organized into Merkle trees, for those of you who are familiar with it. But the basic idea is that you have each file protected by a hash, but you can verify that any part of that file is still part of that file without hashing the whole thing. So I can have like a terabyte long file, but yet it is hashed in such a special way that if I only request a few kilobytes from the middle, I can still verify cheaply that it's part of that same hash. So it's part of that file and not something else. Above this, so these random access files, they don't have any metadata associated with them. They don't have file names, they don't have types, they don't have anything. And above this, we have a virtual content addressed web server. That is what it is. It's a server of data which are addressable by URLs through the HTTP protocol, and they have file types. And above this, we have this swarm-hosted Đapps, and the only cross-layer communication that we have is between the distributed applications. They can access the raw files if they want to. Actually, I would say that it's bad design to do so, but we have decided to keep that possibility just in case you need it. So first, let's look at the bottom layer. So we're discussing this part, how it is built. The storage mechanism is a layer of caches. So if you put a chunk into the store, into the swarm, the first place it gets is a mem store. It's what it is. It's a storage of chunks in the memory of your computer. Then it migrates down to your database, which is your more permanent storage, SSD or hard drive or whatever. And from that, it goes to the network. So it gets distributed to some other nodes so that it can be found if you go offline. A little bit about this net store. So its basic architecture is a DHT, a distributed hash table. Many of you might be familiar with it. The most popular use case for DHTs is the BitTorrent network. Actually, what we have built is in many ways inspired and architected after BitTorrent. There are reasons why we are not using BitTorrent, and we can discuss it later in the questions part. But basically, you push out these chunks, and they migrate towards a few computers that are responsible for the hash range in which that chunk happens to be. So that's basically it. And this network storage layer, that was that cloud at the bottom of the previous slide, has the following properties. So it is using Ethereum's peer-to-peer network communication layer, which comes with some security and network topology guarantees. So we get that for free, sort of. We haven't developed that. We're using Kademlia structure just like the DHT in BitTorrent. But unlike BitTorrent, we're using semi-permanent connections and TCP rather than UDP. This again has to do with the way Ethereum's peer-to-peer network is organized, and it has some advantages which I would skip for now. Again, we can talk about them if you're interested. And the most important question becomes, when you're designing such a distributed system for this particular layer, which chunks to store. So this Kademlia routing makes sure that you will mostly encounter the chunks that are close to your own address. So the basic idea of DHT, for those of you unfamiliar with it, is that addresses of nodes and keys of the data to store in this key value storage come from the same space. So in this case, it's 256-bit hashes, and there's some distance measure defined on them, and typically you encounter, because of the routing mechanism, things that are close to you, both as requests and both as retrieval requests and as storage requests. And what you want to do is to store things that are requested often, so that's what the incentivization layer incentivizes you to do. I will talk about it shortly. And what you will end up having as an emergent property is that you're going to store things that are close to you or which are extremely popular. And you will have maximum resource utilization. So if you set aside 1 terabyte for this swarm, all of it will be used eventually. And basically this emergent property allows you to scale in a very elastic fashion, which is very nice. And I'm not talking about it now, but the failure modes are also very graceful. So about incentives. So there are 2 basic kinds of incentives. One is the bandwidth accounting protocol, which is again modeled after BitTorrent's tit-for-tat strategy, with the added quirk that you can, since we have an accounting system built into Ethereum, which is similar to Bitcoin, that you can cash out of your positive balance. So if you're providing more service than you're consuming, you can actually get others to pay for staying connected rather than disconnecting them. And vice versa, if you just want to consume and you don't want to provide the service, you can still do that, providing that you pay for what you're using. So unlike in BitTorrent, where if you're the only downloader and you want to download something big and you don't want to use upstream bandwidth, then you're stuck. You can only download it slowly. Here in Swarm, you can pay. So if we only had this incentivization, we would have the same problem as BitTorrent has, namely that it's very good for popular content, but not very good for unpopular but important content. So for example, think of your birth certificate. If you would like to store your birth certificate in a distributed file system, which is generally a good idea, if we only had this incentivization, nobody would be interested in serving it because so few people are requesting it that they're not going to earn anything. So in order to incentivize that kind of service, we have availability insurance, by which I mean a smart contract. Okay, this you might not be familiar with, but basically it's a binding promise made within the system, which is automatically enforced, where you can promise to store something and put up a security deposit for it. And if you fail to deliver it, then you will lose your security deposit. And of course, you can sell this kind of availability insurance to people who want to store things that are not necessarily popular. So that's the other incentive structure, and we believe that with these 2 kinds of incentives, we have covered the large majority of interesting use cases. So there's a protocol and the API that comes with Swarm. The BZZ protocol, well, we have this, so everything is named after the theme of bees and hives and things like that. So that's why the protocol is called BZZ. So it consists of the following 4 subprotocols, and it basically deals with forwarding and requesting and accounting for chunks. That's all it does. And we have 3 important APIs available for distributed applications. A JavaScript API, which is accessible from a console, but as well from for web-based applications. We have an HTTP proxy. So from these 2, you can immediately see that one easy and natural way to build distributed applications is to host them right there in Swarm and have JavaScript calls to the API to deal with them. And we also have command line tools. And since we're in a Linux conference here, I would like to say that we're working on Linux level API, so it is going to be something based on Fuse, so that you can actually mount parts of Swarm onto your file system. So let's talk a little bit about the architecture of distributed applications, which are the upper layers above the chunk storage. So the HTTP-based API, it's like a locally running web server. So it's an HTTP where you're basically talking HTTP with your local host or some HTTP gateway to Swarm. And we implement these request methods the usual way. And here's how you are going to see the URLs. So these things here, the first one is the raw API. So this is going to give you a file whose hash is this, without any metadata, except for the file length, of course. The second example, where you don't have this raw thingy, just a hash, is going to give you the front page of a web application which is hosted there on Swarm. If it has an index HTML, then of course you are going to see the front page. This next example, it has a, I think it's called fragment in HTTP parlance. So this is some kind of a state. So the application whose hash I have abbreviated here is actually a distributed photo album. So it's very similar to Picasa, except that it's distributed. And this one is just the number of the photo that you want to be looking at when you're browsing the photo album. So here you can see this kind of API, this kind of URL is the same hash. So this hash protects the whole of the website. So each file in this case is protected by the same hash. You have complete integrity protection, and it's just one image from that photo album. And here you can see that instead of a hash, you have actually a human readable name. That is achieved by a name service built into the blockchain, so into Ethereum, where you can actually register names for particular hashes. So, for example, if you're modifying your photo album, you have added a few photos, then you can register the hash inside the blockchain, and then within a few seconds or a few minutes at most, everybody who's participating in the network will learn that these clipped wing strings corresponds to your photo album, and if they put a, so this would show the fourth image inside your photo album. So that's the HTTP API. Of course, if you modify things, so if you post, post, or delete requests to these URLs, then the root hash is going to change, because the root hash sort of integrity protects the whole thing. One way to imagine how it is done, it's a little bit more complicated than that, but think about inodes of directory files, and this hash is the hash of the inode of the top level directory, and the files are referenced as with their hashes. So this is why everything is connected through a chain of hashes and is therefore cryptographically integrity protected. So one basic distributed application, what I've already described, is a distributed photo album, but this is easy. So we have already implemented this, it works, you can use it, but the reason it is so easy is that there's only one producer and many consumers. So there's no concurrent modification, which is, of course, the difficult part. Changes are infrequent. So if you make some changes and you post them to the blockchain, it's not going to be prohibitively expensive. And latency of a few seconds or a few minutes is perfectly acceptable. So these are the relatively lax constraints of this application, which makes it really easy to implement. So let's look at something that is more complicated, a distributed Dropbox. There's concurrency, there's payment and rewards, and there are security properties. So this is work in progress, we don't have it yet. This is actually my full-time job, I'm working on this particular application right now. it is doable. So concurrency can be taken care of by means similar to the way blockchains are being handled. So there are some modifications in the state which you concurrently do, but then there's some resolution mechanism which is arbitrated through the blockchain. So you should imagine that the blockchain is just the ultimate arbitrator of changes, and you turn to the blockchain only if there's some disagreement between what changes can be done. But otherwise, it's roughly similar to how Git works. So if you know how concurrent changes are handled by Git, it's kind of the same pattern here. And confidentiality and plausible deniability in case of a distributed Dropbox are, of course, of primary concern. One is the security of users, and the other is the security of providers. So, of course, if you want to back up your hard drive on a distributed Dropbox, you don't want the providers of the service to know what they are storing, what's on your hard drive. So that's confidentiality. And on the other hand, if you're providing this service for others, you want to have plausible deniability. So you don't want to know what you're storing, and you don't want to be held accountable for storing other people's child pornography or whatever. And the nice thing about these two things, that they can be done on the very bottom layer, on the level of the chunk store, and everything above it just, it just works. You just get these things as an emergent property from these properties of the bottom layer. So that's the nice thing about the clean architecture, that it becomes relatively easy to reason about it and to show certain security properties. So lastly, we want to, so this is a super ambitious project. So we want to create Web 3, which is sort of better than Web 2 in that there are no big centralized entities that hold the whole world hostage. So we want to do things like Facebook in a distributed fashion. It's hard. It's not that different from a Dropbox. Google is, of course, does many things, but in particular here I'm talking about indexing and ranking. Doing this in a distributed fashion is even more difficult. So in this case, what you will have to do is you will have some nodes that are running these MapReduce-like algorithms for a fee. So there's some, you can participate as a ranking node or as a sorting node for creating the indices. And because of the smart contracts that Ethereum can have, you are sort of guaranteed to be only rewarded if you do what the contract tells you to do. So it's still secure against malicious participants, but it's super difficult. So searching, I do not expect search to be available in the beginning. So probably the way you will search Swarm for a while is going to be some web gateway that is made available to Google, and Google will just index it. But we want to get rid of Google eventually. Now, data sets like Wikipedia and OpenStreetMap, they're interesting because the way they are implemented in Web 2 is actually quite efficient. So both of them, both Wikipedia and OpenStreetMap, have some claims about reality which are actually quite subjective. So Wikipedia is quite useless about, for example, describing events of recent history, and OpenStreetMap is kind of contentious when you have disputed territories. And with a distributed system like Swarm, you can do better than these centralized systems are doing. So you can, so the reasons with that in Web 2 you can't handle these issues, it is because creating a copy of Wikipedia and modifying it a little bit is super expensive. With Swarm, however, you can register your own version of Wikipedia. Moreover, you can have a register of different Wikipedias, because we know that in these cases, typically opinions, they cluster around a few. So in this case, since it's not super expensive, actually it's super cheap to make a copy. It's like Git, you just make another branch. So you can have multiple views of the same issue, and you can actually look up what are the current views, and you can have some reputation systems and so on and so forth. So basically you can have a repository of human knowledge without the official truth. You don't have to have an official truth, and yet you can kind of collect the whole knowledge of humanity. So we're actually very keen on of migrating these two data sets into Swarm. What's the status of our project? We have a reference implementation in the Go programming language. It's not extensively tested, so we had some medium-scale tests with a few dozen and few hundred nodes, but we're still preparing for the large-scale test within the Ethereum community. Our funding comes from, so it's a crowd-funded project, so we're burning money that we have collected as a pre-sale of Ethers, but eventually we would like to move on to various other community-funded methods and to attract, open source contributors. The whole project is currently on GitHub, but of course GitHub is also one of those centralized things that we want to migrate to our infrastructure eventually. We want to conquer the world. It's very ambitious. So here's the GitHub link, and basically that's all I have to say. And if you have questions or comments, you're very welcome to ask them. Yep.
What about conferences?
Conferences. Well, I have been, in the past 2 months, I've participated in 4
they are
conferences.
centralized of sorts.
Oh, online conferences. So online conferences is similar to Facebook. So it's basically something where you put up a content and you allow comments to it and threaded conversations. Yeah, that's one of the use cases that we're foreseeing, and I actually know people who are working on such things. It exists.
Any more questions? Please wait for the microphone for recording.
Okay. My question is, my question is about verification. You told that your storage is Byzantine fault tolerant, and this implies that it can tolerate arbitrary behavior of one-third of nodes. And how do you verify that it can tolerate the arbitrary behavior?
Okay, so very good question. So how Byzantine fault tolerance works? So it is, from an engineering point of view, it is broken down to 2 issues. One is any state of the file system is protected by a hash. So once you have this hash, then you can verify through a Merkle hash tree construction everything down that hash. So every file name, every content of each file, and so on. So basically you have reduced the problem of Byzantine consensus that everybody agrees that clipped wings means this hash. So once you have solved that problem, you have solved everything. How we solve that? Well, that's what the blockchain is for. So the blockchain of Ethereum, it also has a hash tree, a Merkle hash tree in it. And you can write a smart contract where you can register names, and then it's Ethereum that takes care of that part of the consensus for you. So that's the short answer. I think the long answer we'll have to discuss after the conference.
Okay, and looks we have a problem with the microphone. I will ask you to repeat the question.
Yeah, my question is about access control. If someone puts an object into Swarm, how does one control what are other people allowed to do with it?
Okay, the question was about access control. Again, it's a very good question. It is broken down to several things. What you can read, what you can modify, and yeah, those 2 things basically, what you can read and what you can modify. Read access can only be provided by means of cryptography. So you can read everything, but you cannot decrypt everything. So access control on the read level becomes a question of distributing keys. Access control on the finding and modifying level is trickier, but it is about smart contracts. So it's hidden in this name registry thingy. So basically, if you want to upload something to Swarm, you can do it and you will get a hash. The question is that once there's something that everybody watches, for example, your Dropbox, and how can people change the root hash of your Dropbox? And in that case, you need to write a smart contract that outlines the kind of legal state transitions. So which state transitions are legal and which are not. You outline it in the smart contract, and it's the smart contract that will take care of that. So you do that on the Ethereum level, on the blockchain level, and you can say that that's expensive, and you will be right. So probably if many people are going to use it, doing every access control change on the blockchain will not be feasible eventually, but then it becomes a blockchain scaling issue. That has a whole lot of literature and research going on about it, but in this particular case, I think that the solution is going to be similar to what I have outlined with the access control of comments, that as long as everybody agrees that the state transitions were appropriate, they were legal, then there's no question. And only if there's a dispute, then you turn to the blockchain, and the blockchain is going to arbitrate. So you're going to have a smart contract in which you can resolve disputes at a cost. But as long as there are no disputes, it's only the individual nodes that verify that, okay, this state transition is okay, this guy did have the right to add that file into that directory. So that's the answer.
Okay. Next question.
Yeah, so you described the system to be somewhat like Git, which would mean that flipped wings would be similar to a tag of a hash. And that's describing fixed content that cannot change, is that correct? So my question really is then, how do you create content that changes and make flipped wings, the tag name, behave more like a branch where you can update it over time?
So the question was that if you register just a static hash for clipped wings, you cannot have mutable content. And how do we have mutable content which changes over time, right? That's the question. Okay, the most basic answer to that is that you re-register clipped wings every time, which for many purposes is okay. So whenever you change what's clipped wings, you just update it's like changing the head of the Git branch. So the system, as I've said, is very, very similar to Git in this respect. Again, this might become a bottleneck, a scalability bottleneck, to turn to the blockchain each time you change something. But in this case, it's really easy to do a scalable solution arbitrated by the blockchain. Instead of registering the hash directly, you register a public key, which is allowed to modify the hash. And the message that you send to the contract and to everybody else is a nonce and a signature. So you have a nonce, the root hash, and a digital signature. And of course, everybody can verify that without actually turning to the blockchain. So if the nonce is larger than the previous one, and the digital signature conforms to the public key registered on the blockchain, then it is a valid update. And only if you want to, make sure that everybody's on the same page after some time, you actually update the nonce inside the contract, and then everybody will know that nonces that are older than that number are invalid. So that's it. Did that answer your question?
Yes, I think so.
Okay, any more questions? Okay, in this case, we'll say
Okay, one
okay.
I have a second question about latency. Actually, it is typical to have a compromise to have centralized fast system and distributed slow system. For example, you have talked about Google. Google guarantees about 200 millisecond response time for queries. And what latencies are typical for your system, for your applications?
What is the typical latency? Well, it depends on how many resources, what amount of resources you throw at it. So you can have large part of the swarm duplicated on your host if you have a lot of memory and high bandwidth. You can duplicate large parts on your node, and then you will have very low latency for reads. If you have a smartphone with very little memory and you're turning to the network for everything and you have a slow internet connection, then you will have high latency. So it's in many ways up to you. But that's only the read access. Modification access latency depends on the latencies of the underlying consensus protocols. And in that case, we have eventual consistencies. So having things like, if you know, Google has this thing called Spanner, a SQL database synchronized with atomic clocks. Now, it's unreasonable, at least for now, to expect nodes in the swarm to have that kind of thing. So we are eventually, like ultimately, this thing is tied to the Ethereum blockchain, which has an average block time of 15 seconds. So a modification is accepted after a few blocks have been added to the blockchain. So I would say that modification propagation is currently on the order of 1 minute. But some subsystems can work faster than that. You're just not guaranteed Byzantine consensus for time frames shorter than that. But apart from that, you can have faster propagation. Yes, there's one more question.
Hello. After the previous question, a thought came to my mind about CDNs. Do you provide some locality? So, okay, 200 milliseconds from here to USA turn around. So if I make Facebook using the storage and show many pictures on the page, about 30 pictures, yeah, then I'll have very long time of downloading because number of connections are usually limited in the browsers to one origin, 6 now. Something about this, could you tell us?
So the question was how well Swarm performs in the role of a content distribution network, a CDN. So is it location aware, is it network latency aware, network proximity aware, and so on? And yeah, that's the crux of your question, right? So the answer is that part is built into this layer. So it has a Kademlia topology, and for those of you who know how Kademlia works, you have for each proximity class, which are called buckets, you have a number of peers. And there's a preference built in to peers which are closer to you in terms of network round trip times. So the emergent topology of the swarm network is somewhat aware of the network latencies, and we hope that it functions well as a content distribution network. However, so project status, this is one thing that we have not tested yet. So it's there by design. We hope that it works, but we don't know for sure yet. That's the answer.
Okay. We have a couple minutes for the last question. If you have this, still doesn't work. Okay, in this case, let's say thank you for this presentation.